Good afternoon, welcome back. This is lecture 29 and let me quickly recap what we did last time. I will just give you a quick run through of our lecture. So, our last lecture was basically had to do with maximum likelihood code symbol of decoding of the convolutional code, and it really represented more or less the end of our discussion on the GDL. So, we were looking at the GDL and we were applying it to the problem of decoding of a convolutional code. And earlier when we discussed convolutional code decoding, we had talked about the Viterbi algorithm. So, now this is an alternative algorithm which is called the BCGR algorithm, and although it can be derived independently on its own, what I did here was I showed how you can actually generate it using the GDL. So, the entire lecture was more or less devoted to showing how the GDL in a certain setting gives you the BCGR algorithm. And so, our starting point was the description of the convolutional code in terms of what I told you was a Bayesian network. And here is the MPF formulation of the maximum likelihood code symbol decoding problem. We identified the local domains and the local kernels. Then we constructed the junction tree out of this, and then once you have a junction tree, then the and our objective function, let us say in general our objective function would be to compute the likelihood of all the message symbols. We took a particular message symbol U2 and then we showed how we could compute the objective function. So, the second step after constructing the junction tree is to actually pass messages. Now, if you treat it like a single vertex problem, then you orient all the edges towards that single vertex and pass messages, and that is what we did. So, we had the F1 of S1 and the F2 of S2. So, our schedule looks like a forward message passing and then a backward message passing sequence. Both of them are iterative. So, in the forward direction you have F1 of S1 on the second iteration becomes F2 of S2 and so on, and we showed what that iteration looked like. And then I gave an interpretation in terms of the trellis for a particular example convolutional code. I showed you that what it really means is that you are actually doing a matrix multiplication where you are actually looking at something on the left and going to the right. So, it is a matrix multiplication of this type. Then the backwards algorithm is also very similar. So, again here you have G4 of S4 evolves to G3 of S3 because you are going backwards, and the relationship between G3 S3 and G4 S4 is given by this. Again it can be interpreted as a matrix multiplication, and this is what we did. So, both forward and backward are matrix multiplication steps, and then the final step is to actually compute the objective function. So, let us say that you want to compute this, and at this point what you have is you have access to F2 of S2 from this side and G3 of S3, and you want to compute the objective function. So, what you do is you pass messages through this, you marginalize, multiply by the local kernel, and you end up with an expression like this. So, you end up with this, and that more or less concludes the algorithm. Now, it is possible to interpret even this calculation on the trellis, but for lack of time I will not actually do it. However, what I might do is just add a note here. Since you will have access to these notes, I do not think there is any harm in that. So, we will just say that this concludes our discussion of the BCJR algorithm. Okay. And then there's another comment I actually wanted to make in this connection, which is that if you wanted to switch from the BCGR algorithm to the Viterbi decoding algorithm, then I am going to say it in words and I will summarize it very quickly. Then it turns out that you can actually formulate the problem in a very similar fashion, the only difference being that whereas here your operations, you are operating in the sum product semi-ring, you would be operating there in the max product semi-ring. So, wherever you have a summation, you would actually have a max. Okay. And apart from that, all the operations are very similar, and you could again have a forward and a backward message passing. Now, you might say in the Viterbi algorithm there is only message passing in the forward direction. Why is it that we have backward? The reason the difference arises is because let me just take you perhaps to a sample lecture from earlier. So, here you have the trellis. So, when we looked at the Viterbi decoding algorithm, we saw that the algorithm only moves from left to right. So, you may be a little bit puzzled, how come you have a forward and backward? Well, the reason is that in the Viterbi algorithm, we carry at every recursion, we compute metrics assigned to the nodes at a certain node level, and we moved from node level to the next node level, okay? And we keep going from left to the right. But we also do something else, which is we retain the memory of the path leading up to a particular node which has the largest metric. So, these are the survivors. So, not only do we keep the survivor metrics, we also keep track of the survivor. For example, if this was the surviving path, we keep track of it. In the GDL version, you do not keep track of it. So, what you do is you only keep track of the survivor metrics. So, you go forward with the survivor metrics, you come backward with the survivor metrics, and then once across a link, you look at the metric on the left, metric on the right, find the best connection, and then decode one symbol at a time. Okay. I realize this is a little bit fast, but essentially it tells you how you can actually do Viterbi decoding as well. Okay. So, with that, I will start today's lecture. And so, our recap is completed. Discussion of the BCGR algorithm. Okay. A very quick recap, and then I will just make a quick remark here that the Viterbi algorithm can also be recovered using the GDL, DL. One simply operates in the max product semi-ring in place of the sum product. In the algorithm, the essential difference lies in replacing the summation operation by the max of operation. Okay. And for lack of time, I will actually stop here and introduce our new topic. So, our topic for today is LDPC codes. So, what does LDPC stand for? So, LDPC stands for low density Okay. So that leads to the question, what do you mean by low density? And so let me begin by trying to explain that. So these are block codes, and every block code has a parity check matrix. So supposing you look at a parity check matrix, then as we know, typically if you are talking about a 742 code, so let me put that assumption here, or rather let me do one thing here. Let me move this a little bit down. And say let C be a 7 or more generally an NKD, an NKD linear block code. So as you all know now, by now, this is the block length, this is the dimension, and that is the minimum distance. Now typically when n is long, you are really interested in codes where k is some fixed fraction of n, and similarly d. So typically okay, so I guess I need to create some more space for myself. So typically when n is large, and I have already explained to you why large block lengths are of interest when you want reliable communication. So when n is large, the codes of interest, the codes of practical interest, have k by n equal to r, where r is some integer lying between 0 and 1, and d min by n equal to delta for some delta lying between 0 and 1. So, what you should interpret this to mean is that when n is large, you can think of this as n tending to infinity. It is not really infinity, it is more like you might in practice have codes whose block length is 16,000, 32,000. So, it is large. And then you are not interested in codes where the dimension is 3 and the length is 16,000. It is more like k by n is some appreciable fraction. Okay? So, this r is some fixed fraction between 0 and 1. Often r is half, for example, or r is 1/3 or 1/4. So, what that means is that as n tends to infinity, so does k. And the same goes with the minimum distance. You would typically like your minimum distance to also grow fractionally, although this fraction could be much smaller. Okay. Now, the way we defined our parity check matrix, this in the context of this notation, that is when you have an NKD block code, your parity check matrix would be of size n minus k by n. So, it would be a matrix of this type. So, what that means is that the total number of entries is on the order of n squared, and in a random parity check matrix there would be an equal number of zeros and ones, and therefore, the number of ones in this parity check matrix would be on the order of n squared as well. Okay, so, let us make a note of that. Thus, in a typical parity check matrix, the number of entries is of order n squared. Okay, so, you can say that it is big O of n squared, and since entries are typically again equally likely to be either 0 or 1, the number of ones would be on the order of n squared as well. Okay. So, this is where LDPC codes are different, because LDPC codes, the number of ones is not of order n squared, but rather of order n. So, however, in the case of an LDPC code, the number of ones in H is of order n. Okay, so, that is one difference. Then again there is a second difference. The second difference is that when we talk about a parity check matrix, so this matrix is of size n minus k by n, and when we introduced parity check matrices, we said that these are really generator matrices for the dual code, and so therefore, the rows had to be linearly independent. Okay. However, with LDPC codes we relax that assumption. So, that means it is meaningful to talk about a parity check matrix without requiring that the rows be linearly independent. Okay. a second difference. A second difference in the case of LDPC codes is that rows of H need not necessarily be linearly independent. However, we still require that the rows of H generate the dual code CPUP. This can be used to show that once again this implies that the null space of H is precisely the original code H. Original code C. Sorry. Okay. Now, there is a particular class of LDPC codes that I will now introduce. A D sub V, D sub C regular LDPC code is one in which each row of H has DC ones and each column of H contains DV ones. In this case, your H is not n minus k by n, but simply let us just say that it is an m by n matrix. The reason I say that is because, see, this earlier when the rows were linearly independent, then I could say that the number of rows had to be n minus k because the dimension of the null space was k, and that is the dimension of our code. But since now we have relaxed the requirement that the rows be linearly independent, what this means is that the rank of H is less than or equal to m. Therefore, the dimension of the null space of H is greater than or equal to n minus m. Therefore, the dimension of the code is greater than or equal to n minus m. Okay. Therefore, k is greater than or equal to n minus m. Now, if you are talking about the rate of the code, k by n is greater than 1 minus m by n. All right. Now, in the case of a DVDC code, what will happen is that every row of this matrix will contain precisely D sub C ones. Okay. On the other hand, if you look at a column, every column will contain D sub V ones. But now you can count the total number of ones either by counting row by row or counting column by column. So, that means the total number of ones in this matrix on the one hand is m times dc, on the other hand it is n times dv. Okay. So, let me just put that down. Therefore, m times dc is equal to n times dv. Therefore, m by n is equal to dv by dc. So, this is our second equation. So, going back over here, we can say that therefore, k by n is greater than or equal to 1 minus dv by dc. This is 3 and it comes from equation 2. Okay. There is a representation of an LDPC code which takes on the form of a graph. So, let me show this to you through example. Okay. So, I will finish drawing this figure, take about a minute or so more, and then I will explain. Okay, so this graph here represents the code and is called a Tanner graph. And what this graph is actually telling you is that on the left side these nodes are called variable nodes and these nodes are called check nodes. Okay. All right. And this is really another representation of the parity check matrix in the following sense. So, you should think of this as though, and I will put this down on the next page, you should think of you should keep this picture in your mind. There is a parity check matrix. This matrix, it will be called H, is a 5 by 10 matrix. The rows of the matrix are, let us say, labeled as A, B, C, D, E, and there are 10 columns. So, the columns are numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And what this graph is telling you, so perhaps I should draw and what this matrix is, this graph is actually telling you is that in row A, remember that the rows are in correspondence with the letters and the columns are in correspondence with these numbers. So, there are 10 columns and 5 rows. It is saying that in row A, there are ones in columns corresponding to 1, 2, 3, 4, 6, 7, and that is indicated by the lines joining 1, 2, 3, 4, 6 and 7. So, you will notice here that as far as every row is concerned, every row is connected, every check node is connected to 5 variable nodes. And on the other hand, if you look at every variable node, it is connected to exactly 3 check nodes. So, as a result, so let us try to fill in some entries of the parity check matrix. So, row A has 1, 2, 3, 4, 6, 7, which means that we would have a 1 in 1, 2, 3, 4, 6, 7. Okay. And then if you look in terms of across rows, where is 1 connected to? 1 is connected to A, it is also connected to D and to E. Okay. So, in terms of columns, there is a 1 here, here. Okay. So, wherever the remaining symbols are 0. Okay. So, in this way you can fill up the entries of the matrix, and what you will notice is that this is an instance of a DV-DC regular code, because every row will turn out to have Hamming weight 6 and every column has Hamming weight 3. So, this is an instance of a dV equals 3, dC equals 6, regular code. Therefore, in terms of the minimum distance, in terms of the rate of the code, we can actually say that the rate is greater than 1 minus dV by dC, which is 1 minus 3 by 6, which is equal to 1/2. So, therefore, the rate of the code is greater than or equal to 1/2. So, the reason we are not able to be exact about it is because we do not require that the rows be linearly independent. And so, in LDPC terminology, this is called the designed rate of the code. And typically people work with the design rate of the code instead of trying to figure out what exactly is the rate. Okay. So, this Steiner graph has a particular structure that the nodes on the left are connected through links only to nodes on the right, and similarly the nodes on the right are connected through links or edges only to nodes on the left. There are no links between nodes on the left or nodes on the right. So, this is an instance of a type of graph which is actually known as a bipartite graph. So, we will make a note of that. Okay. And so, now we found another representation for the code, a graphical representation. That is, instead of defining the code in terms, it is still a linear code, it still has a generator matrix, it still has a parity check matrix, but instead of describing in terms of the matrix, we will now have a graph, and this graph will tells you uniquely defines the code. Okay. So, it tells you that the parity condition that must be satisfied, there are 5 of them. For example, B lays down the rule that symbols x3, x4, x5, x6, x7, x8 together must have even parity. Okay. So, that is how you interpret this. And in terms of the graph, the fact that this is a dv-dc regular code manifests itself in terms of the degree of the nodes. So, every node on the right has degree equal to 6. So, the degree of the node, a node is equal to the number of nodes to which it is connected through edges or links. So, each node on the right has degree 6, each node on the left has degree 3. Okay. So, we will make a note of that also. Degree of each node on the left is equal to 3, and the degree on the right is equal to 6. All right. And now you might ask, okay, what does what is the reason for such a restriction? And I will try to give you a partial answer. One thing you notice is that if you look at the total number of ones in the parity check matrix, the total number of ones on the parity check matrix, every one corresponds precisely to an edge because it belongs to a certain row and a certain column. So, the number of ones is precisely the number of edges, but the number of edges is equal to the number of either the number of rows times the degree of a node on the right, or equal to the number of nodes on the left times the degree of a node on the left. Now, since the degree is fixed, it is a small number like 3 or 6, and typically in LDPC codes, when we talk about dv-dc regular codes, the block length could be very large, but we will still fix these degrees. So, what that means is that the number of ones in the matrix is automatically some multiple of n. So, it is order of n. For this reason, these are called LDPC codes. So, that is our next comment. Note that the dv-dc constraint implies that the total number of ones in the parity check matrix is equal to n times dV is equal to m times dc, and hence is of order n. Okay, since dV dc are fixed and independent of n. So, if you think of the number of ones as a fraction of the total number of entries in the matrix, it is order n divided by order n squared, which is very sparse, and that is why these are called low density parity check codes. Okay, so that explains the terminology, but why would you want low density? Well, the thing is that what you are actually going to do is you are going to decode this code by passing messages on this graph. You are going to pass messages from along the edges of this graph, and you are going to do this in the following way. You are going to start with some messages that are passed from left to right, followed by messages that are passed from right to left, and then left to right, and so on. Every time you start a round of message passing from right to left followed by left to right is called one iteration. Okay, so there is an initial phase in which you go left to right, but then thereafter every iteration constitutes a round of message passing from right to left and back from left to right. Typically the number of iterations is some fixed number like 20, maybe 50, depending on what level of accuracy you require. So the number of operations, and every time you pass messages you do some operation at each of the nodes. So the total number of operations is proportional to the number of nodes, proportional to the degree of a node, and proportional to the number of iterations. But if you fix the number of iterations, and since the degree of a node is fixed, the total number of operations is linear in the number of nodes on the left, which is linear in the length of the code. So that means that if you can actually decode this code simply by a sequence of message passes from left to right and vice versa, then you have been able to decode the code in linear complexity. Okay? And that is the beauty of LDPC codes. Their greatest strength is the ease with which they can be decoded. And now you might think, well, but does that come at a price? To some extent, yes. The answer is yes and no. It depends on what you are looking for. These codes in terms of minimum distance may not always be the best possible code that you can get for that block length. However, they make up for it in performance. It turns out that for practical purposes the performance is pretty good. Okay? Not always, but for most instances. So this class of code is fast becoming what people call the ubiquitous error correcting code. That is a code to be used in all situations. They are becoming very, very popular and likely to be widely in use because of the ease of decoding. So let me just add a comment to the effect that the graphical comma message passing nature of the decoding algorithm in the case of an LDPC code implies that the complexity of the decoding algorithm is proportional to the number of edges in the Tanner graph of the code, and hence is linear, and I think it is worthwhile putting some exclamation marks in the block length of the code. So, it is this fact, it is this single fact which makes these codes of great practical interest. Now, you might ask, well, where did this name Tanner graph actually arise from? So, Tanner is it's called Tanner graph after Michael Tanner, who is a coding theorist out of out of the University of California system, who so these codes actually these codes have an interesting history. So, they were these algebraic and convolutional codes that were in existence up till the late 80s, until in early 90s a class of iteratively decodable codes called turbo codes surfaced and were proven to have superb performance, and they were iteratively decoded. And around this time there were a group of people who discovered these LDPC codes and showed that they could also be decoded iteratively. And then people realized that these are really codes that were discovered back in the 60s in a PhD thesis, in a beautiful PhD thesis of information and coding theorist Robert Gallagher. Okay. So, they really are a rediscovery of something that appeared in the 1960s, but the technology at that time was not ready to exploit the contents of the thesis. So, Michael Tanner was one of those who rediscovered LDPC codes, but then he went a little bit further and he actually added some structure. He introduced this graphical interpretation of the decoding algorithm. So, he contributed much to the theory, and that is why these are called Tanner graphs. Now, okay, so that now you must be wondering what exactly is this message passing decoding algorithm like. And the nice thing about it is that coming from our background, so we have just come off by looking at the GDL. So, it turns out that the underpinnings of this algorithm from a certain viewpoint, so different people explain the decoding algorithm in different ways, but I am adopting a viewpoint adopted by some others, including the authors of the paper on the GDL. That is, that the GDL is in some sense provides the underpinnings of the message passing algorithm, and I will make that a little bit more concrete. If you will recall, in an earlier lecture we looked at decoding the 74T code, 742 block code. So, let us see if I can actually pull that up. Okay, here we go. This is what I was looking for. So, let me okay. So, here is the junction tree. Here is the junction tree of the 742 code. Okay. So, what I want to actually tell you is that the same graph can be redrawn in a slightly different manner. Okay. So, if you will recall, this particular code had parity check matrix which is of this form. Okay. So, this parity check matrix had 3 rows, and each of these parity checks is associated to a node in this graph. There are 7 code symbols, and each of them is associated to a node in the graph. I can redraw this graph in the following way. I can actually, as in the fashion of a Tanner graph, so I can put down the variable nodes on the left, I can put down the check nodes on the right. So, this corresponds to 1, 2, 4, 3, 4, 6 and 4, 5, 7. And if I draw edges like we did in the case of the Tanner graph, we obtain the Tanner graph. So, this is the Tanner graph representation of our earlier 742 code. And in a way, you might actually think about it. Let me see if I can show these to you side by side. Perhaps if I copy this page, that might happen. Okay, here we go. So, here you can actually see the 2 graphs side by side, and when you look at this, you can see that basically you can interpret this as a redrawing, because this 1, 2, 4 is A, 3, 4, 6 is B, and 4, 5, 7 is C. Okay. So, we will make that more clear. Let us write here A, B and C. And it turns out that there is more to it than that. In fact, it turns out that there are various possible message passing algorithms that are adopted on a Tanner graph to decode an LDPC codes. But there is one which goes by the name belief propagation, which mimics more or less the messages that are passed in our junction tree. Okay. So, in fact, you already have seen an instance of the kind of messages that are passed in this graph. Anyway, since we have just about a minute left, let me summarize. So, what we did today was introduce a new topic, which is LDPC codes, and I tried to explain why these are of interest, how the name low density arises, how you can estimate the rate of the code, introduced a graphical representation called the Tanner graph, and then I told you that messages are passed on this graph to decode the code. And I also pointed out these messages in some sense are not completely new, because a certain type of message passing is similar to the message passing we encountered on the junction tree. Okay. So, with this I will close, and we will take this up in the next lecture. Thank you.